Hi, this is a second part of a two-part video. If you haven't watched the first part and you would like to see it, please check out the link on the screen right now or somewhere in the description. That part is all theoretical, this one is all about the practical aspects. So yeah, let's dig in. Okay, so we made it to the breadboard. We are here because we want to play with these devices, a transmitter, a receiver and a transmitter that work on 433 MHz using ASK encoding. There are many tutorials out there that teach you how to wire them up to an Arduino and use a library such as Virtual Wire or Radiohead or other libraries out there in order to send a simple message between two Arduino boards. In this video I want to do something different. I want to start slowly, no Arduino at all, and make short experiments and build up knowledge as we go forward. First of all, we need to power our circuit, so I'm using one of these nifty little boards that take either 5 volts from an USB or between 7 to 12 volts from a battery pack such as this one with a jack connector. Has on board voltage regulation, so you always get out a nice 5 volts. Now let's place this on the breadboard. One thing you have to be very careful about, and which I did a boo-boo and actually burned one of these devices the first time I did this, is to watch the polarity, the plus and minus, and don't put them the other way around like I'm about to do now. So plus minus and then minus plus. Flip this and make sure the polarity is right. Okay, now let's power this little board from a USB cable from my laptop or from a phone charger or whatever. I'm using my laptop. So yeah, I got power. Now let's take the receiver first of all. Let's look on the back of the receiver and we see the pinout. So we have ground, VCC, so they're in the margins, and in the middle either of these pins is data pin. You can use either one of them, doesn't matter. So let's connect this. Let's place it on the breadboard and let's power it up. I'm gonna use a black wire for ground. So which one was ground? The one on the left. Come on. Yeah. Okay, so ground goes to ground, and I don't have a red wire nearby, but it's a reddish one, orange red something. Let's hook it up to VCC. Now let's connect a wire to either of the middle pins, like I said, which is the receive pin. And now let's power this up and let's see what's receiving. No Arduino, no nothing. Now you do need to have an oscilloscope for this operation though, and since these are quite expensive, you may not have one, but I do, so we can do this experiment. Let's connect another wire to the ground over here so we can probe easily. And now let's see what we can see on the output on the data pin. So we see some noise, but rather nothing. Now happen to have these car keys around. You can use your own car key or any device that happens to transmit on the, like I said, on 433 MHz, and let's press it, and voila, we see a signal. Let's zoom in on that. Okay, let's adjust the scale. so we can clearly see a bit pattern. Our receiver is working. Now let's try to transmit something. So let's take the transmitter. Again, if we look at the pins, we see, or at least I see, I don't know how well you can see from the camera, VCC pin is to the right, ground to the left, and in the middle again the data pin. In this case it's only one pin. So we put this on the breadboard. So VCC to the left. I think there's a drill somewhere in the apartment building. Anyway, making the connections. Okay. Now, for the sending, the simplest thing we can do is simply connect the pin to VCC on a short burst. So let's see how that looks on the oscilloscope. So we connect the pin and we see something being sent. Now, instead of a single transition, we actually see lots of squiggly transitions, which doesn't feel right. So one thing I'm gonna do now, and which I was gonna mention later anyway, it's better to actually power your devices from a battery whenever you're dealing with signals, because if you're powering from the laptop, for example, or from the power outlet, you inadvertently introduce like the 50 Hz sine wave from the power cables in the walls. If it's not filtered well by the system, you automatically get it in your signal. So with a battery it's much cleaner, so I'll do that now. Let's take a look again. Just the oscilloscope. So I don't know if you can see, but already the signal is way cleaner than it was before when it was connected to the computer. And now again, if I try to connect it, see that something is happening. Okay, now it's more like it. Come on. So we kind of see a square wave and a bunch of ringing whenever I connect the wire. Right, but this is not very professional. It was just to prove a point that you can detect the active transmission. Now let's do it a little bit more professional, and let's use the Arduino to send a pulse, let's say every 10 milliseconds. For that, let me see if I can zoom in on the screen. Okay, so we have a simple program. We just defined a read and a write pin, and for now we set the... Actually, we forgot to set the pin mode for the write pin to output. For now we don't need the serial. So we have our pin number 9 set to output, and in the loop we simply write every 10 milliseconds. Actually, wait, I forgot something. It's supposed to be like this. And then we write a 0. Then we wait another 10 milliseconds, then the cycle repeats. So let's connect our Arduino. Compiling the sketch. This is an old laptop that I don't use anymore, except for electronic work. In case I do something wrong and, I don't know, maybe fry the USB port, I wouldn't mind. Okay, so the program has been written to the Arduino. Let's check it out. So let's use 2 wires. And see if the program is doing what we want. So I want the ground and I also want pin 9. And I want to see what's going on over there. And if we take a look, see, we have a square wave at 50 Hz, which is just about right. So let's feed this in to our transmitter. By the way, if you don't have an oscilloscope, there is a neat trick you can do with the Arduino and the serial plotter. I'll show you that later. But now let's do what we wanted to do. So first things first, you should always make sure that you connect your Arduino's ground to the other part of the circuit ground. They need to have a common ground, otherwise nothing works. Then we take our signal from pin 9, there we go, and we put it, actually this wire is not long enough, use this wire even though it's the same color, and I put it to the input over here. Come on, get a little closer. Okay, and now let's probe again. We connect the oscilloscope to the circuit ground and to the output of the receiver device and see what we get. And lo and behold, we're getting what we're transmitting, the 50 Hz square wave, which we created simply 2 digital writes separated by a delay of 10 milliseconds each. Let's also try to change the frequency to make sure it's not a glitch. Remember, the wall power installation also works at 50 Hz, so to be sure it's what we're sending that goes through, let's say every 3 milliseconds, and upload this. And let me change the view, and now we see 166, come on, 0.2 Hz, and again it's a square wave. So yes, it is indeed the one created by us, and it works flawlessly. Let's do another experiment. Let's increase the time by a lot to 500 milliseconds. So we have a slow changing square wave, a slow changing pulse, or however you want to call it. We upload this and we adjust the scale, and we see something interesting. We send pulses which are 500 milliseconds long. What we get on the oscilloscope are in fact pulses which are just 92 milliseconds long, so about 5 times shorter. And actually, if doesn't matter how long we want to make our pulse, I think this is the maximum it will get transmitted. Now, why is that? Well, in fact, I don't know why that is, but based on speculation and what I've read and what I understand so far, it has to do with the fact that inside the transmitter, the way the various parts of it are capacitively coupled. So if we were to imagine we have the tuning and filtering section over here, so here would be like the antenna, and then we have like an amplifying section or amplifying block, and then other blocks. Here is something like this, so it's like we have a capacitor. I mean, most likely we do have an actual capacitor. And what's the purpose of this capacitor, and how does it in fact affect our signal the way it does? Well, just a moment, click something here. So let's look at the single transistor classical circuit when you want to amplify a small signal. So we have our transistor over here, like base collector emitter. So here's the power rail, this is the base, this is the emitter resistor, this is the ground, this is the plus, I don't know, 5 volts let's say. And usually and here is where we take our signal out, and usually both when we introduce our signal and when we output our signal we use capacitive coupling. Why is that? Well, for example, on the input we want the transistor to be in the forward active area, so to have at its base around 700 or 600 millivolts ish. How do we do that? Well, we use this resistor divider over here with the proper values, such that we create a permanent DC bias voltage here of about 700 millivolts. But then we also want to bring in our signal. Now, unless we would have this capacitor over here, this would not work. So the capacitor actually helps to combine the signal, which is usually very small, and it's AC, so it's changing all the time, with the fixed DC bias voltage, and to get like a neat superposition of them. Now, the downside to having this capacitor is what we observed. So what happens, for example, if we have a input signal that goes like this, then on the capacitor we're gonna have something like this. Just a moment. So it would be something like this. And so on. And if the capacitor were, its capacitance would be very small in accordance to the time it takes for the signal, so the frequency, we might even have something like this, where it drops way before the time where the signal changes, and it stays there. Then it goes up again very quickly, then drops again very quickly. So in essence, it's exactly what we observed. So our long 500 millisecond duration square wave actually only had about 92 millisecond pulses due to this capacitor somewhere in the circuit that's out of our control, out of our reach. So the point is, slow signals will not get through unaffected. We need to send fast signals. So the shorter this distance is, this, in general, the bigger the frequency, then we're okay. At small frequencies, not okay. But then you might ask, how would we send, I don't know, like 1000 zeros, ones? So this would be like a 1, a 0, a 1, a 0. This would be like 2 ones, and then zeros. This would be like 3 ones. And if we were to send like 1000 ones, then even if we had a very small frequency, we will still end up sending a huge block like this with the constant DC voltage. The solution to that is different encoding schemes, such as Manchester encoding, where, for example, instead of encoding 1 like this and 0 like this, the two levels, we actually encode the 1 as a high and a low. This is a 1. And we encode a 0 as a low and a high. And in that case, even if we have, let's say, 3 ones in a row, we would have up, down, up, down, up, down. If we had 3 zeros in a row, we would have down, up, down, up. So, and if we have, let's say, 1, 0, 1, we will have up, down, then down again, up again, and then we have a 1, up, down. So, and the actual boundaries would be something like this. So this would be a 1, this would be a 0, this would be, what would be this? Oh, another 1. So in a nutshell, that's about it. That being said, let's get back to the Arduino and our circuit again. Actually, let's not. Let's leave it for a third part and wrap things up here, because I think it's enough content for this video. Hope you liked it, thanks for watching, and see you in the third part. Bye!